And what we did towards the end, we actually the operations we defined addition, subtraction, and of course we started with multiplication. Now multiplying or multiplication of vectors is different than for instance numbers, as you might expect. So usually we have different types of vector multiplications. We introduced one which is the simplest type of multiplication, which is multiplication of a vector with a scalar in general. Okay, so I'm going to give here some examples as well as the theory in general, but also we will actually focus on the so-called three-dimensional vectors in solving the examples or the exercises. Okay, so vectors, operations, vector. Before I start with vector operations, I will not explicitly mention that always, but whenever we are doing to define any operation, it doesn't make sense if the vectors are from different dimensions. That means if you are adding up vectors, they must be from the same dimension. For instance, if one is three-dimensional vector, then the other must be three-dimensional. Same applies to multiplication and so on. So it doesn't make any sense to talk about any other operations involving vectors from different dimensions. Okay, so we defined in general, we said that we will just refer to a vector as a small number, small letter with an arrow on top of it, and then you have components depending on the dimension of vector. So let's talk about the general case here. Okay, so let A be a vector. And let's take another vector and B also be a vector. Another vector of the same dimension as you see here. This is n, this is n. And let's take a constant and k be a real number, which is a constant. So last time we defined addition, adding, and subtraction of vectors. What we do logically, component-wise. So if you want to add A and B, you add A1 to B1, A2 to B2, and so on. Now, regarding multiplication, we will distinguish three types of multiplication. The easiest is multiplying with a scalar. Okay, so the first type of multiplication, if I just multiply the vector, let's say A with a scalar or constant, so I will be having here k multiplied by the vector here up to an, and what I'm going to do, I just expand this constant to all entries or components of the vector. So here you end up of having A1k, A2k, and so on. And notice here that this multiplication here, maybe I just add a dot here. This is a real number multiplication because k is a real number, and then A1, A2 up to an are real numbers. So this is a real number multiplication. This one here is the multiplication of a vector with a scalar. Okay. Any questions? Okay, if you have any questions, please just write on the chat. Okay, now we said that the nature of vectors requires other types of multiplication, and we can't just do it like we did for numbers. So here we will basically focus on two types of multiplication other than this one, of course. As you see here, this is not involving vectors. So when we talk about vector or multiplication of vector with another vector, we have two different multiplication, let's say, rules. The first one is the so-called dot, or sometimes it's also referred to as scalar, or sometimes even it's referred to as the inner. We'll tell you in short, product of vectors. Okay, so dot or scalar product or inner product of vectors. So let's assume that the vectors from there, so A and B, that we defined earlier, and then A dot B dot product or scalar product of B is defined as the magnitude of A times the magnitude of B times cosine of theta, where theta is the inner angle between the two vectors. That's why it's also called inner vector. As you know, if I have here two vectors, let's say this is A, this is B, and here we can determine two angles, right? This is the angle. So this is the angle we are looking for, because there is obviously another angle, which is the outer angle. We are talking about the shortcut here between the two lines. Now, the magnitude of A, the magnitude of B are constants, and if you still don't know how to evaluate it, I will just remind you, given the vectors there. So the magnitude here is defined as, let's do it for A, for instance, or maybe we can do it for both. Square of each of the components of the vector, okay? And then taking the square root of that. And notice that this can never be negative, because we are just taking the positive square root here of the so of the sum, and it can't be, because if you are squaring, it's positive, so it can't be negative here. And the same here, the magnitude of B is similarly defined as B1 squared plus B2 squared, and so on until Bn squared. Okay, so that means with this scalar product, we can do many things. For instance, as you see here, this equation involves three different parameters to the on the right side, one to the left side. So all in all, we have four parameters. This is one parameter, and if you know three of them, any three of them, you can find the third. Okay, so for instance, I can give you two vectors and ask you to evaluate the angle between the two vectors, and so on. So note here, to evaluate the angle, it's difficult to keep track of here. Okay, note, to evaluate the angle theta between the two vectors, which is the inner angle theta, what we do, we rewrite the equation. So if you just, let me frame this one here, if you just solve this or just rewrite it, so just put cosine to the left here. So cosine theta is equal to the product the dot product A dot B divided by the magnitude of A times magnitude of B. That means to evaluate theta, you need to, if you take the inverse of both sides, so you just, it follows here that cosine theta is this amount. So theta is equal to the inverse, cosine inverse of this ratio here. Okay, AB, bear in mind this is the dot product of vectors, and this is here the magnitude of A times the magnitude of B. Where cosine inverse also in some calculators, some reference boxes referred to as arc cosine. Arc cosine is the same as cosine inverse. I hope that everyone at this stage is capable of using the calculator to evaluate this amount here. Anyone has problems with that? Here you have to just be careful that the the scale of your calculator is set correctly. That means it could be, of course, degrees or radian. So just make sure that if you want it in degrees, that it's set correct. Usually in calculators, there's a button you can switch forth and back between degrees and the radians. Okay, any questions so far? No questions? Okay. Now I will ask a question. Using what we introduced so far, okay? If given two vectors, can we or how can we find out whether the vectors are perpendicular, or sometimes it means orthogonal? I don't know which term you are used to, meaning that the two vectors, they have just one is they have just a right angle in between, okay? Or vectors are parallel to each other. Okay, so parallel to each other, meaning anyone has an idea? So if I have here two vectors, let's label this A, this B, this A, this B. Okay. Tell me what would you suggest here? Imagine you only know the dot product or the scalar product, and I give you two vectors, and I tell you, are these vectors, for instance, perpendicular to each other or orthogonal? What does that mean? What does that mean? What about this angle here? No idea? Rajo, do you have any idea? You are online? Yes. Said, no idea? What does it mean that two vectors are perpendicular to each other? No idea? You have heard about this term, perpendicular, or it's just here in this graph, they form a right angle, right? I'm sorry, I can't hear if anyone is saying something, but Rajo, you do have no idea what perpendicular means? What is the angle between two perpendicular lines or vectors? 90 degrees, right. Cosine, exactly. Cosine of 90 is equal to 0. That means here, notice that this amount here in the denominator, it can't be negative. It can't be 0, sorry, because we have vectors and they have positive magnitude. Now here they are perpendicular if and only if the cross product, sorry, the dot product is equal to 0, okay, out of this formula. So whenever you are trying to check whether two vectors are perpendicular, it's enough to check whether the dot product is 0, okay? However, is it clear? Because this is 90 degrees and cos of 90 is equal 90 degrees, or pi over 2 is equal to 0. However, if they are parallel, what is the angle between the two parallel lines? Is 0, right? And what is cosine of 0? Cosine of 0 is 1, exactly. So cosine here is 1. That means here, what does it mean? Cosine of 0 is 1. That means here the dot product, so this amount here is 1. If the dot product, the numerator and denominator are equal, right? So this is the meaning. So with this dot product, we can find the angle, we can decide or check whether they are parallel, they are perpendicular to each other. And notice that here parallel, the angle can be 0 if they have the same direction. If one is opposite to the other, then the angle is pi or 180, and both have the cosine is 1. Okay. Now, how to evaluate the dot product of these two vectors? Let me just write the same vectors there. Let's see. So how to evaluate the dot product of two vectors? Okay, so evaluating, you can see it now. I will just zoom it out. Okay, evaluating dot product. How to evaluate the dot product? Again, just to remind you, given two vectors, a vector that has one, A1, A2, AN, and B has the coordinates P1, P2, up to Pn. Again, I just remind you that this is only possible if they have the same dimension. It doesn't make any sense if you just have, actually not only for this product, any operation on vectors from different dimensions. Now here the rule is that A dot P, the dot product, is the sum of AI times BI. This is here the real number product. I equals 1 to N. That means here A1 is multiplied with B1 plus A2 multiplied with B2 plus, if you are not familiar with this notation of sum, AN. Clear? So this is how we evaluate the dot product. Maybe we take an example here at this stage. Questions? Is it clear? So let's take an example how to find out the. I didn't prepare an example here, but we can take any example actually. We had one this morning. Question in the worksheet. Let me just see if I have it here somewhere. Uh, okay, this is a good exercise now since we have the whole theory. Let me check. Okay, so here we have the question. Okay, so let's take it as an example. So given the vectors, three vectors, let's say A equals -1 here in the worksheet. It's written with I, J, and K, and 3, and B equals to 3, 4, and 5. Okay? The task here, find the angle theta between A and B. Okay? So the thing here is we have the vectors. Let me just write the equation again. So the formula here is A dot B as vectors over magnitude of A times magnitude of B. Okay? Now, we want to evaluate theta. That means if we know this ratio here, then we will plug it into the calculator and evaluate cosine inverse to get theta. So that means here we need to evaluate the dot product. But before that, let me just remind you how to evaluate the magnitudes here. The magnitude of A equals to, we have here the coordinates of A. We square each coordinate, add them up, and take the square root. That's all. So here, you have to be careful here if you have negative. I saw that some students, they just have problems with this arithmetic, multiplying with negative, another negative, squaring this. So I saw really students who plug in -1 and try to find the square, and then they will end up with having -1, because if you don't put it in parentheses, it will be squaring only 1. So here, please just, if you have a negative, enclose it, then parentheses, plus 2 squared plus 3 squared. And this is equal 1 plus 4 plus 9 under the square root, and this is equal to square root of 14. Okay, so the second thing here is to evaluate similarly, the magnitude of B. Here we don't have negative, so no need to enclose it in parentheses. So 3 squared plus 4 squared plus 5 squared. This is equal 9 plus 16 plus 25. And this is the square root of 50. Okay, so far, any problems? So we are done with the two parameters here in the denominator. Now, how to evaluate the dot product? We are going to use this rule here. I hope you still can see it, this rule. So this rule tells me multiply this number with that number. Add it to the result of multiplying this number with that number, and then the result of adding this number to this number. Okay? And here again, you have to be careful if you have a negative. So here A dot P, evaluating the dot product of three-dimensional vectors. So we have -1 times 3 plus 2 times 4 plus 3 times 5. And this is equal to minus 3 plus 12 plus 15. Did we make a mistake here? So the vectors again, 1, 2, 3, 3, 4, 5.
Yes, sir. You put 2
Okay,
times
so
4 equals
this is
12.
8. Okay. So 5 plus 5 is 20. Okay, so the dot product is 20. Please, I want your feedback. Is it clear for everyone? Evaluate the
Yes, sir.
magnitudes of three-dimensional vector and evaluating the dot product of three-dimensional vectors.
Yes, sir. It's clear.
Rana, I can't hear you. Sorry, I can't hear you. I don't know here. We have problem.
Yes, clear, sir.
Okay, just write something. Okay. Questions? Now this is actually always the same. If you have different dimensional vectors, then the procedure is the same. Then you have different values, different. So for instance, here, if you have a 4-dimensional vector, then you just square the 4 coordinates and then take the square root. If you have multiplication here, you multiply the components out, add them up. This is the dot product. Now, still, we didn't solve the question here. We need to find out the angle. And to evaluate this angle, actually, we need to evaluate this ratio and plug it into our calculator and see. Okay, so now theta. So this ratio here, cosine theta, is equal to, I'll just write it here, maybe just to remind you the formula, over the magnitude of A, magnitude of B, and then this is equal to 20 over square root of 14 times square root of 50, and so anyone can evaluate this ratio for me? Anyone can evaluate it? Exactly. Okay. Thank you. So we have here 0.7, let's say 559. Okay. And if you take the inverse of that, 0.57, no, 7559, 7559. The cosine inverse of this amount here, you get theta, which is equal to 49.40, roughly 40.89 degrees. Okay. Okay, so very straightforward. You have one unknown or one variable, 3 values that are known, dot product, the magnitudes of both vectors, you evaluate the cosine, and then you plug into your calculator this to get the cosine inverse, which is the degree. If you have it in different or another scale like the radian, then you have to be careful there. All right, so this is about the dot product. A very important note here. This is actually an important note, and it is a major difference between this dot product and the next vector product that we are going to introduce is the following. Notice that the way we evaluated the dot product, we are summing up real numbers. So that means here that the ultimate outcome here of this is a real number. Okay, this is a very important remark here. The result of dot product is a real number. Okay. If you don't have any questions, let me move to the next type of product, which is the so-called vector product, or sometimes it's just called cross product of vectors. So the second type of product here is a cross product or sometimes it's called vector product. Okay. Now this one is for vectors in R3, three-dimensional vectors. Okay. Now, before I start with that, I just want to maybe okay, let me just define it, and then I will give you some geometric interpretation of that. But then we need to spend some time in today's class evaluating determinants, because this is a very important topic here that will be needed in many of the applications that we are going to evaluate during this course. So this is important. If you have any problems with evaluating determinants, in particular three-dimensionals, maybe sometimes some four-dimensional determinants with some zeros, for instance, then I will urge you to if you studied it before, just refresh your memories, or if you didn't, just try to experience or to solve some problems. After today's class, I will introduce a couple of methods how to evaluate it. So determinants is an issue here, but before that, let us define the vectors. A cross B is called the cross product of the vectors, of course, of the same dimension, A and B, and it's given by now here I will just write it. So I will just write the magnitudes here, A, B, sine theta, and here maybe some vector, let's call it U, where U is the unit vector perpendicular to the plane that contains A and B. Not done yet. Now, imagine, I don't know, it's difficult maybe here in the projector. So I have the vector A and the vector B, okay? And assume this is theta. So let's just, now here, this vector U is just a vector perpendicular. So this page of paper is the plane that contains these vectors. Let's say this is vector A, this is vector B. Now, if this is, I hope you can see it. If this is the plane that contains this, these two vectors, so A and B, a vector that is perpendicular to it, unit vector means it's vector with one magnitude 1. It could be this vector. So this is the pen, which is perpendicular to this plane. I hope you can see it. Or it can be also from down, the vector perpendicular from the other side to this paper, okay? So here to avoid the ambiguity, because we have two such vectors that could be perpendicular to any plane, then we will use the so-called use the unit vectors perpendicular to the plane that contains A and B, and it is determined using the so-called right hand rule. What is the right hand rule? You place, I hope I have graphic here, because in the class I could demonstrate it better, but let's see, maybe I have some. Okay, here you go. I have the, yeah, so this is the graph here. I hope that everyone can see it. Now the right hand rule says you place, so it's difficult to demonstrate it here. So vector A, vector B are these two fingers, and then the thumb will be pointing to this direction. So this is the right hand rule. Vector A, vector B, the same plane, and then here you have the thumb pointing up from this plane. So this is what is meant with the right hand rule. And this is, of course, to avoid ambiguity. As I showed you, you can have this is the plane here, the shaded area containing the two vectors. A vector that is perpendicular can go in this direction or in the other direction. So to make sure that we can determine this uniquely without any ambiguity, we just use this rule. Okay. Questions? Now, this is the definition of this product. To evaluate it, it's a little bit not difficult, but it's a little bit more tedious. So it has applications in physics and in mechanics, for instance, momentum, where it's just the cross product of the force and the distance of the power, the arm, and so on. So now the thing here is what is the I will just remind you about three vectors. What we will be agreeing on now is very important for evaluating this type of product. Okay, so let's agree on the following. You remember we said that if we have the three-dimensional plane here, we are talking about three-dimensional vectors. So let's assume I have this three-dimensional plane. Now, if I have the three vectors, you remember the unit vectors, I will take unit vector in each direction. Okay, I will take unit vector in each direction, and this unit vector we introduced actually last lecture, if you remember, when we talked about the so-called what was it called, the generating set of the plane, you remember, or of the generating set of the vector space. And at that time, I introduced to you these three vectors. I will remind you now. The first vector was 1, 0, 0. Okay, so first of all, let's agree on the axis here. This is X, this is Y, and this is Z. Now, a vector that is exactly 1 unit here, a vector that is exactly 1 unit here, a vector that is exactly 1 unit here. Okay, these vectors are called unit vectors in each direction. Now you remember we called them I don't know, E1, I think, E2, E3. Also some textbooks they call it E sub I, E sub Y, E sub Z, or in some literature they just refer to them as X with the hat on top of it, bold, and Y or Z. Now I'm going to use a notation that we will agree on. We will call this unit vector in direction XI. This one in direction ZJ, and this one K. So let's start maybe at the beginning. We will use this hat on top of it to show that it's a unit vector rather than it's a scalar. Okay, now what are the coordinates of these vectors? This vector here is 1 unit on X and all others are 0. So this one is 1, 0, 0, its coordinate. You remember these vectors? This one, 0, 1, 0. Here along Z, I have 0, 0, and 1. And you remember we showed that these vectors generate yes, exactly. This is exactly what is meant. Yeah, the right hand rule is to, we said that this is important here, that this is important, that I hope you still can see it here. The outcome of cross product is a vector. Okay, it's a vector, and a vector has usually magnitude and direction. Now this part here will evaluate the magnitude of this vector. In short, we will see what is the interpretation of that in geometric interpretation, but it needs a direction. So this U here, it will show us the direction, how to let's say decide which direction this dot product, this cross product goes up or down. So we use the right hand rule. Exactly, this is what Mahani, this is what you wrote here. Exactly. Okay, so this vector is just a unit vector that showed us the direction, and it's evaluated using the right hand rule. Okay, Now, please, this is now important because from now on, you will find these notations everywhere, but we will be just using this notation. So, and we said that any vector in R3 here is a linear combination of these. That means these three unit vectors generate all the R3 vector space. That means any vector in R3, and we had some examples, can be split down as linear combination of these three vectors. So from now on, for instance, a vector, the vector A equals 2, -3, and 4, let's say. Okay, we can write it as 2i minus 3j plus 4k. I hope that everyone is fine with this notation. Okay, so from now on, I will just use this to refer to the unit vectors in I, unit vectors in X direction, J is unit vector in Y direction, K is unit vector in Z direction. I hope this is okay for everyone. So by default, whether you are given the vector in this form or in that form, this means that it's two units in direction I. This means 3 units in direction -G. Of course, it's in the negative Y direction. This means 4 units in direction Z, which is K. All right. Okay. Now, how to evaluate the cross product? Now I will give you the formula, and then we will, as I told you, spend some time in evaluating the determinants. Okay, now U or A cross P. Let me maybe here start with something. Okay, so let me start with vectors. Now we talk about 3-dimensional vectors, A and B 3-dimensional vectors in R3, where A equals A1, A2, A3, and B equals B1, B2, B3. Okay, then the cross product is defined as A cross B is equal to the determinant of, here in the first row, I will place I, J, and K respectively. So the order here matters. This I is the unit vectors in X, Y, and Z directions, these 3 vectors. And then I will just place the 2 rows containing the coordinates of the vector. So here A1, A2, A3, B1, B2, B3. So this is here the determinant. What is a determinant? A determinant is a constant real number that determines a value. That's why it's called determinant for each square matrix. So here, determinants here, it's only defined for square matrix. What is square matrix? It's a matrix that has same number of rows as columns. So here we have 1, 2, 3 rows, 1, 2, 3 columns. So determinants are always defined for square matrices. Okay, any other matrix that is not, that is not given as squared matrix, it makes no sense to talk about determinants. Okay, so this is how we are going to evaluate the cross product of two vectors. Place the unit vectors here on top, and then the two vectors, two lines, and then we will be getting a 3 by 3 determinant that is possible to evaluate because it's a square matrix. Now, how to evaluate it? I will give you two methods for evaluating determinants. Evaluating determinants. Now we will forget for a while about the vectors and just focus on evaluating determinants. I will give you two methods. The first method is the so-called by reduction, and it was introduced by famous German mathematician Leibniz. Now the n formula for an n times n matrix it's a little bit complicated, but I will give you the so to speak the shortcut for evaluating 3 by 3 determinants. Now before that, we define a 2 by 2 determinant as so. For a 2 by 2 determinants, the determinant is evaluated. This is a definition by we cross multiply this diagonal. Okay, so it's A times D as real numbers here, and then subtract this from the result of this multiple. So this is a negative. Here it doesn't matter which C time, because you know real numbers multiplication is commutative, so AD or DE, but let's just stick to this direction and C times B. So this is a rule, and we will use this as a termination rule for our reduction. What we do here, if we start with a determinant, this is what Leibniz did. If you have a determinant, then you will delete one row, one column, and then you get a determinant which has a smaller dimension and so on. Don't worry, this is my attendance. You can. Okay, this is something I do, but attendance alone is just not enough. You need to also pay attention and make sure that you understand what we are doing here. It's more important. Okay. Okay, so this is the rule for 2 by 2 matrix or determinant. Now, how to evaluate the 3 by 3 determinant using this method? Let's again here take A, B, C, D, E, F, G, H, I. So let's assume this is 3 by 3 determinant. Using this method, we will be doing the following. The first thing here, we will be just, we can do it according to any row, but here, because we will use it for the cross product here, we placed IJK in the first row. Let's do it along this first row. Now here, Leibniz rule says that this is alternating positive, negative, positive. So this is the first rule. So here for 3 by 3, the first part of the formula is positive, then the middle one here is negative, and then it's positive. So if you have 5, for instance, then it will be alternating. It means positive, negative, and so on. For this, you need to know that positive, negative, positive. Okay? Now, what's Leibniz rule saying? That's why it's called reduction or recursive. It says we take this element here, A, first element. So we will be picking up elements along this row that we will be evaluating accordingly. We take this A, okay? Then we multiply it with the determinant that will remain after eliminating this row and column where A is located, okay? That means here I'm going to eliminate this row and this column, and I hope it's clear for everyone that we are left with this determinant here. Okay, so as you see here, in this step from a 3 by 3 determinant, we are left with E, F, H, I, which we can evaluate using this formula here, okay? So it's only one step. Now, the second one here, don't forget the negative here. B, I will multiply it with the determinant that remains after deleting the rows and columns where A is located. And I hope that everyone can see I'm left with D, F, G, I here, okay? D, F, G, I. The last one here, I move to the last one here, I have C. And if I just delete this row and column, I'm left with D, E, G, and H. Any questions regarding this step? Okay, so positive, negative, positive. Take this number, delete the row and column where this occurs, take the multiply it with the remaining 2 by 2 determinant, and then the same for the others with the negative sign for this middle term here. Now here, how we can evaluate this? So remember that this evaluating each of these determinants, it means this multiplied with this minus this multiplied with this minus multiplying these out, and so on. Okay, so let's expand this and see what we get. So it's A multiplied by EI minus HF minus B times DI minus FG plus C times DH minus, sorry, let me just write it here, plus C times DH minus. Mustafa, are you saying something? DH minus GE. Okay, that's it. This is how we evaluate determinants using this method. Okay, any questions?
It's clear, sir.
No, sir.
Okay, now we turn to let me see. Yeah, maybe before that, I want you to I want to show you the graph here. This one. Okay, I want to show you the geometric representation of that one. Mm. The interpretation of the cross product, I told you that if you have two vectors and then you connect them together, you will be getting a triangle, right? You get triangle. However, I don't have the graph here. I don't know. Maybe I can show you this one instead. A, B, C. Okay. So now, as you see here, these two vectors, we can span with these two vectors something that what we call the parallelogram. I hope you can see it here. Parallelogram. And the area of this parallelogram is determined as the magnitude of the vector that is the result of the cross product of A and B. Okay, so the area of this parallelogram is just the magnitude of this vector. So if you are asked to evaluate the parallelogram spanned by two vectors, then you just evaluate the cross product and then calculate the magnitude. Notice that the cross product will deliver a vector, but the magnitude is going to deliver a constant number. And then in this case, we have the constant number, and taking the absolute value, we just make sure that this is a positive number, with it will be the area of this parallelogram. Let me just here just distinguish this. So this is the area of the parallelogram. Now the area, if you want the area of this triangle here that is spanning these two vectors, then the area of this one, it will be half of this as per the properties of the parallelogram. Parallelogram actually is similar to rectangle, but it doesn't have right angles. So each opposite sides are equal, but these angles are not right angles. However, if you connect any of the two diagonals, it will split the parallelogram in two equal rectangle, into equal parts, and the area of this is equal to half of the area of the parallelogram. Okay. Okay, so this triangle is half. So if you are evaluating the area of the triangle connecting the 3 points, or the spanned by the two vectors, then you just evaluate the cross product, evaluate the magnitude of this cross product, divided by 2, and you are there. Okay. Questions? No questions? How to evaluate 3? It's not possible. It's not possible. So I'm just saying, go back to the script. It's still here. It's underlined. Okay. A square matrix Square matrix, it means an n by n matrix. That means it has as many rows as columns. And it's actually not defined for other type of matrices, okay? So it's not possible. It's not defined. Okay? Bahani, okay? This is, you mean with that 3 times 2 determinant, that determinant that has 3 rows and 2 columns, or the other way around, it's not possible. Okay. Now, there is another method for evaluating determinants, which is called the method of Saros, I think. Okay, this method, I will just give you the general idea about it, and then maybe we will solve an example. Okay, so let's take the same. This method says you just duplicate the first 2 columns. Okay, so you have here A, D, G, B, E, H. Okay, then you have 2 different diagonal, three diagonals each direction. Let me just try. Maybe I need to just do this. Okay, so this is first, second. So I have 3 diagonals that are, if you like, top right. So from top to the right, falling from top to the right. And I have 3 other diagonals that are falling from right down.
Sir, what's
Okay.
the word above?
Now I will just tell you how to evaluate the determinant now. Now, the Saros rule says the following. You evaluate the determinant. First of all, you duplicate the first 2 columns only. Then you have the right down, or you can say right up here, depending. So this falling from left to right, and this one falling from right to left. Now this one, you multiply out the terms here, add it to multiplying out these, adding to multiplying out these. So the red side, multiply them out, add them up, subtract all these from the same here, multiplying these 3 elements, these 3 elements, these 3 elements, adding them up. Okay? So I will just write it here as so we will demonstrate it in an example. I'll just write it here as this one minus this direction, okay? So notice that this one first, this right down, and then left down, and adding them up, you will be having the same result. Let's take an example here. Maybe this is the best thing we can do here, and we can do an example and see. After this example, you will find out that this method is maybe much easier. I don't know which one you prefer, but let me just find out the example. Okay, so by the way, I'll just go. If I have here two vectors, let's say this is vector 1, vector 2, and then I have this. Then I think you know that this right angle here is just the magnitude of this is A, for instance. Then this is the magnitude of A sine theta. And I think at school you learned how to evaluate the area of the parallelogram by just if you like cutting this triangle here and then completing this to a rectangle. So if you want to make it as a rectangle, if this is B, then the sorry, B here, then the area of this rectangle is just the magnitude of B times magnitude of A times sine theta. So maybe this will explain the formula for the cross product, just from geometric perspective. Now let's take an example and see how to solve it using both methods. Okay, evaluate the determinant. Let's say A is the matrix, and this is 1, -2, 3, 2, 0, 3, 1, 5, and 4. Okay, we are going to evaluate the determinant using first reduction method. Sorry. So determinant of A, method 1. Okay. Now, as I told you here, we take this element, positive, negative, positive. Take this element, then we will end up of having this determinant. Okay. So it's 1 times the determinant that is left here is 0, 3, 5, and 4. If I cover this line and this line, I left with this determinant. Now minus, here I have -2. Always when you have negative, just enclose it within parentheses. Okay, now if I cover this column and this row, I am left with the determinant 2, 3, 1, 4. And the last one here is 3 times. I'm left here, if I cover this one, 2, 0, 1, and 5. Okay, so far, any problems?
Sir, what's the word on top?
Okay. Now, the next thing, I'm going to apply the rule for evaluating a 2 by 2 determinant. Simply this one, multiply it out, subtract it from that one, and so on. And here, be careful to the negative signs, please. I see some students are making errors there. So 1 times 0 minus 5 times 3, 15. 2 times 4 is 8. So here again, negative, and this is -2 times 8, 2 times 4, minus 3 times 1, or 1 times 3 is 3, plus 3 times 10, 2 times 5, minus 0. And this is equal to minus 15. So here it has too many negatives, so this will give me 5. Then you have negative, negative, positive, right? So you have a positive, and you get plus 10, right? Plus 10, negative 10 times negative. And then this one here, it will give me another 30 plus. So 40 minus 15 is 25. So this is the answer using this method. Is that somehow clear? Any questions regarding this method? Okay. Next, we will evaluate this same determinant using the other method, the so-called Saros method. And again here, we of course logically will expect the same answer, right? So the second method, it says simply, I will write here the determinant as always. So 1, -2, 3, 2, 0, 3, 1, 5, 4. And here I will be placing 1, 2, 1, -2, 0, and 5. This column and that column. Okay, now here, let's see the diagonals here. So this is the first diagonal here. I multiply out these numbers, add them to multiplying out these numbers and adding them to multiplying out these numbers. So let's evaluate that. So 1 times 0 times 5 plus -2 times 3 times 1. So this dot is not decimal, it's multiplication, plus 3 times 2 times 5. Okay, so this is the right-hand side of the first multiplication, and I'm going to subtract this from the result of multiplying out these falling diagonals. Okay, so let's start here from the left. So minus, so here I have 3 times 0 times 1 plus 1 times 3 times 5 minus 2 times 2 plus minus 2 times 2 times 4. And this is all subtracted, okay? Now let's see, simplify here a little bit, see what we get. Okay, so this is 0. This is -6. This is 30, right? 0, 15, and 16 negative. Okay, so we are left with -6 plus 30 minus 1, 30 here. And this is 24 plus 1, and this is 25. Okay, so as expected, here also we got the same answer. Okay, any question? Which method you like, you prefer, you like more, you think it's easier?
Which method
No, I
was easier,
can't
sir?
hear you, but in any way, yeah, second one, of course, it's easier. But please, when you evaluate the cross product, it's better if you do it using the first one, because we place the several the 3 unit vectors in the first row, and then we want to find the vector in terms of these 3 vectors. So we want to find the component for I, J, and K, and that's why I urge you to use the first method to evaluate at least the cross product of two vectors. Okay, so let's take a break now, and then after the break we will just learn a couple more things related to products of vectors, like the triple product, and then how to interpret this, and then we will start with the complex numbers. Okay, so we will be back on 11:30. Okay, 11:30 we continue.